You might tell me that, okay, this Bellman equation is going to let me, moral of the story, to the value or action value for one particular policy that you have, needing to go, time, nested time expectations. Just do some recursive algorithm. But what if we want to look at the optimal values and optimal policy? Can we do it directly using that? Because here we need to know the policy. And once we know the policy, we can use Bellman equation to compute value, right? But what if we want to find the optimal value, right? Indeed, we can simply play around with that equation to just find it for the optimal policy without needing to know it in advance. How is it possible? Let's look at this. This is what I told you. This is what is still on the board. So if you have the action value for one given policy, then you can find the value for that policy, right? The value of the policy is written in this form using the policy itself and the action value, right? Now, one thing that you might pay attention here, this pi here. This pi is a probability, right? So what is its value? Can it be negative? Can it be more than 1? What's going to happen if I add this pi over different a? It's going to add up to? If I add up pi am given s over different m from 1. So if I remove this guy. What is the summation? It's 1. Great. So this is a probability function, right? Between 0 and 1, it adds up to 1, right? Now, let's use this very simple fact to see how this value is going to behave if we do know this action value. So I consider this axis. Here, when you go right, the value is larger. When you go left, the value is smaller. Okay? Now, I just show action value for one particular action with a red dot. Okay? If I have m different actions, how many of these dots I'm going to have? M different dots, right? So they're going to look something like this, right? Some of them have more action value, some of them have less values, right? Everybody's clear? No magic, nothing weird, right? Now, what's going to be this value v pi of s? This is eventually the average of these red points, right, with respect to policy. I don't know what the policy is. I don't care about that. But given this diagram, can you tell me where is the area where my value can land? Can it be here? Can it be here? Can it be? When you have a bunch of values and you average them with any weights, can it be anything more than the maximum or minimum values? No. It's going to definitely be somewhere between the maximum and minimum values, right? So if you average all of these points, your value is going to be somewhere between them, right? Everybody's clear? No? Okay. This is simple, right? So let's just use this fact. So this value is definitely, whatever that is between the maximum of the action values and the minimum of the action values, right? Everybody's clear? So, meaning that when you are in one state, if you do know the action value for all the actions, right? Value of all the action in this state, then the value of that state obviously is somewhere between the maximum action value and the minimum action value, right? Good. So, if we use that, we can simply use one constraint for the optimal values. So when I play with the optimal policy, what's going to be my value? This is the maximum ever possible value, right? Right? We define the policy, the optimal policy, to be the policy that when I am in one particular state, the value that I'm going to collect afterwards with that policy is the value ever, right? Play with any other policy, if I change my policy, the value that I'm going to collect is going to be smaller, right? Everybody agrees? Cool? So what could be that maximum possible value? look at this guy and tell me, what is the maximum possible value? Maximum action value when the action value is computed for what? Which policy? I'm talking about the value of the optimal policy. Say, I don't know what is the optimal policy. Say, optimal policy exists, right? If I want to know the value of that maximum optimal policy, that value can be at most the maximum value, action value of the same policy, right? Everybody's cool? So it means that when you are playing with the optimal policy, right, then your value is going to touch the maximum one, which is exactly the maximum value, right? So this means that this guy can be the maximum action value among all the possible actions when you are still playing with the optimal policy, right? Again, you don't know what is the optimal policy yet. You're going to know it soon. But the point is that if you are playing with that policy, one thing that you are sure is that the action value computed at any state, when you maximize it, you must see the value of that state, right? If you don't see the value of that state when you maximize it, then this is not the optimal policy, right? Everybody's clear? It's just 2 lines of discussion, I know, but it needs a bit of time to digest. Everybody's clear? Halfway clear? So, if you play with one policy, pi, right? What you know is that the value of your state, so you're in one state. Always think about my dummy grid world, right? If you're in one of the cells, the value of that cell, whatever that is going to be somewhere between the action values, right? Maximum and minimum. It means that if you think about that cell and you say I do action 1, 2, 3, 4, any of those actions, then I'm going to get one value, right? Action value, 1 Q, right? And my value at that particular cell is between the maximum of those action values and minimum of those action values. Now, if I claim that I am playing optimal, like I'm playing with the optimal policy, my value is supposed to be the maximum one, right? And the maximum value that I can take is the maximum action value when I just search among all of the actions, right? So this means that when I am playing with the optimal policy, my value at that particular state gonna be the maximum action value around all the actions, right? Now, I still have not told you what is the optimal policy, but one thing that you right now is that if I claim that I am playing with the optimal policy, you can check this, right? You can use Bellman equation to find the action value. You can use Bellman equation to find the value function. And you can go for every single state, check if the value of that state is really the maximum action value. If this is the case, then I am right. I am doing optimal policy. If this is not the case, I'm lying. I'm not playing with the optimal policy. Clear? Questions? Definitely. We're going to talk about that. We always have, not like most of the time we have multiple, right? Questions? Yeah.
It feels like if I give you a non-optimal policy and you do this, then there may be a way to figure out what the optimal policy is.
Definitely.
Seeing which is the maximum action.
This is policy iteration. What you said is just the policy.
Feels counterintuitive. Like, how are you, like,
No.
policy to figure out the action?
No. I am talking, I say that this is the optimal, if you play with the optimal policy, then this should satisfy, right? What you said that if you play with another policy, it might be a way to improve it, make it better. Right, that is the case, and this is what we call it policy iteration. You start with a random policy, you improve it, and gradually you're going to converge to the optimal policy. This is what we're going to do hopefully on Friday. Okay? So, but everybody sees this constraint now, right? Okay. Now, one thing that you might ask me is that, is there any guarantee? I mean, right now I told you if I play with the optimal policy, this thing should happen, right? But you might ask me, is there any guarantee that this optimal policy exists? Like we can't do really this guy. The answer is quite simple, yes. You can definitely write down the optimal policy. What is the optimal policy at every single state? As long as I know the action value function, I'm going to do the action which gives me the maximum action value, right? If I do that, then that pi is going to be 1 exactly at the action that whose action value is maximum, right? And my value is going to be exactly the maximum action value. Again, if you are in one particular state, you have a bunch of possible choices for action. If you do know what is the optimal action value, meaning that what is the optimal value you're going to get if you do this action, the second action, the third action, action, then what is the policy? Just find the action which gives you the maximum optimal, and then you keep doing that, right? So at every single state S, you just search among every possible action, and then you're going to take the action whose corresponding action value is maximized, right? This is your optimal policy. That guy always exists, right? Everybody's clear? Now, if you got no question, I have a question. Do you see any problem in this formulation? I do know what is the optimal value function. I do know what is the optimal policy. But what do I need to know in order to write these two guys? What I need to know to write down V star and pi star? Please tell me. I mean, just shoot in the dark. Maybe it just works. Optimal action value. I need to know Q star, right? Tell you how you can find Q star, right? Because again, if you want to know Q star, you need to know the optimal policy, right? And then you put it in the Bellman equation, correct? So the cat is just biting its own tail, right? But we can get rid of that issue, that final issue. How we can do it? Then we can simply just put these guys in the Bellman equation, and then you suddenly see that you don't need to know the policy. How can I do it? So first, let me just write down the optimal constraint. So this is the optimality constraint. It says that if your policy pi star is the optimal policy, then it would maybe look like this, right? So it's going to be, this is the optimal action value, and this is going to be 1 at the optimal action, or the action which gives you the maximum value, and then your value should also look the same, right? This is the optimality constraint. If I claim that this particular policy is optimal, then you can check this condition and tell me whether I'm lying or not. But if you want to just start from scratch and write down the optimal policy, you need to know this Q star. How you can know this? Well, let's do this together. Now, this is the Bellman equation that we had before, right? I told you before. Bellman equation, if you just forgot, just take it from my side. The Q function, the action value, is written in terms of the immediate reward plus the average of the value at the different states, right? Now, if I have optimal policy, if I'm playing optimal policy, that policy is one policy, right? So the Bellman equation should also hold for that equation, right? For that policy, right? Meaning that if instead of Q pi, I replace Q star here, and instead of V pi, I replace V star. This is still going to be the case, right? Everybody's clear? Now, this is Q star, right? Q star written in terms of V star. And then I told you before, just let me get back here. Can I write down V star in terms of Q star? Yes. The optimality constraint tells me that if you know Q star, you know V star, right? Everybody agrees? right? So what I'm going to do, I'm going to say this is Q star. If I maximize it over all A values, this is going to give me V star, right? So let me do that. So V star is going to be maximum of this guy over all possible actions, right? Everybody agrees? I didn't do anything. I just used the optimality constraint. Instead of Q star, replace the right-hand side of the Bellman equation. Everybody agrees? Okay. If you agree, look at this guy and tell me if you need anything to compute V star. Do you need anything to compute V star? Do you need to know the policy to compute that? Yes or no? No. This guy is the immediate reward. It does not depend on the policy, right? It says that you're in a state S, you do action A, right? So you can compute this one. That's easy. V star is your unknown, right? So you're going to keep it as it is. And this guy, the probability of going to the next state, given that you're in one particular state and you do one action. It does not depend on the policy, right? It's just depending on the MDP, right? So this is one equation for a state S, right? You can write n different of these equations for the n different states that you have. N equations, n unknown. You know the optimal value, right? Everybody's clear? This is what we call it the optimality Bellman constraint. So you essentially do not need to know the policy, the optimal policy, in order to find the optimal value, because when you put inside this equation, policy shows up nowhere, right? And this means that the optimal value at every single point, at every single state, is depending on the other states through this equation, right? Again, you write down n different equations, n different unknowns, you're going to solve it, and you end up knowing your optimal value. Everybody's clear? Questions? Right? So this is a fixed point equation in terms of V star. You're going to solve it for V star, and then you're going to find optimal value. Now, if you got no questions, say I found the optimal value through this equation. What should I do next if I want to know the optimal policy? If I know the optimal value, can I find out the... Yes, Bellman equation for any policy, including the optimal policy, is going to take me from the value of that policy to the action value, right? So for the optimal policy, I know the value, so I'm going to know the optimal action value. If I know the optimal action value, can I write down the optimal policy? Yes? Problem solved, right? Everybody's clear? So once you know MDP, you can write down the optimal Bellman constraint to find out the optimal value function. From that one, again, you use Bellman to get to the optimal action value function. From that optimal action value function, you just build one constraint, which is a policy, which is the optimal policy, right? So that's the whole story, and I'm gonna explain it in a bit of more details next time because we don't have any more. So next time we're gonna solve this optimal equation for the dummy grid world. We're gonna build the optimal value function, and from that we get into the optimal policy. Questions?